Continuing on with the idea of potential energy, but now we're going to extend it to the electric potential energy. So let us go ahead and write nothing has changed. We're going to have this minus F dot dl equals UB minus UA, which implies that F equals minus the gradient of U. Okay, all right, but now in particular, we already know some things about this F. What is this F equal to? It is equal to QE. Okay, so now we could say we have a gradient of a potential where we have minus, let's make this minus QE dot dl equals this UB minus UA, the change in potential energy. All right, well, is Q going to change? No, Q is whatever force whatever charge we happen to put in this area, so that doesn't change during this. So we can pull that Q out, and we just have E dot dl is equal to this UB minus UA. But it turns out that for most things in most of the time when we are interested in looking at potential energy in electrostatics, we are actually looking at interested in looking at the potential energy per charge. So what we'd like to do is just divide this by charge. So if we divide this by Q and this by Q, we can come up with a new thing. This just cancels. We have E dot dl. Okay, and this now equals, now we're going to define this new thing, which is potential energy per charge. We're going to define this as just potential, which we write as V because it's expressed in volts. Or so the voltage, the electric potential, and voltage are just two different ways of saying the exact same thing. Okay, so don't get confused by that. So this is just VB minus VA. Oops, and I did forget my minus sign now. Okay, VB minus VA. All right, so all right, so now let's just. This is why I'm kind of hesitating, because right now this is pretty much it. That's pretty much it for the whole chapter. If you combine this, what you got in this lecture, with what you got in the previous lecture, everything is contained within that. And remember, the only thing that matters is this difference. This is the only thing that drives things. I mean, you can see that that's true just from this equation, because this says how much the energy changes in the system, how much work is being put into a system or coming out of a system, and the only thing that matters is this potential difference. It doesn't matter if this is 10 million volts and this is 999,999, or if this is 0 volts and this is minus 1 volt. It's the exact same. It doesn't matter what the absolute value of these things are, only the difference. However, we will have to play some games here where for certain problems, we'll have to assume something about where we want the voltage to be equal to 0. We're just going to set this so it's equal to 0. Okay, let's go ahead and look at one specific case for a uniform electric field, because that's going to give us one more definition here that we're going to be able to use. If this E is constant, so let's just say I've got some region of space. I've got some region of space here, and this is just a region of space. And within this region of space, I have a constant E that's just E0 in some certain direction. And so if I am looking in this certain direction, this will also be my DL. My DL will be in that direction. And so my E dot dl is just going to be E0 integral of dl. So let's go ahead and set up a coordinate system. This is here, and we're going to go out to some point here, which is x. Okay? So now let's look at what this gives us. E0.dl minus E0.dl equals VB minus VA, which I'm just going to call this delta V. Okay? So delta V. So E dot dl equals delta V. Well, where are we going from? We're going from well, here we're going from 0 to x. But to be more general, let's just say we're going from some x of 1 to some x of 2. And so we have x2 minus x1. Well, I probably should use B and A again, but it doesn't matter because the important point is that we're just defining this as delta x, right? So the change in x between these 2 points is just delta x. And so that's E0 delta x equals delta V. Or E0 equals minus delta V over delta x. Okay, so for regions with constant electric field, this is true. The integral formulation of this is, well, this down here is always true, but the integral formulation, but this is only true if you're in a region of uniform electric field. However, if you are, this now gives us a very, very convenient way to calculate the electric field strength if we know the potential difference, and the distance difference, or the potential difference if we know the electric field and the distance, or the distance if we know the electric field and the potential difference. Okay, so this is a pretty handy thing to think about. And remember, once again, can't have electric field without a charge, can't have charge without an electric field, you can't have an electric field without a potential difference, you can't have a potential difference without a charge. They're all tied in together. If you have one, you must have the others. Okay, that's that for this one.